Hey everybody, happy Wednesday. Welcome to the ENCOR study group. I actually am coming to the ENCOR study group with some exciting news. I actually passed the ENCOR yesterday morning. I took it for the first time, and for those of you who are like, well, wait a second, Jeff, don't you teach on the ENCOR? How have you not taken that exam? Well, the entire time we were putting together ENCOR material for CBT Nuggets, all of the testing centers were down because of COVID. And they hadn't started online testing yet, so there was no way for me to actually go take the ENCOR before we released the ENCOR material, which is never ideal. It's not how we like to do things. I'm working on my DC core content right now. I've already taken the DC core. Definitely helps to know what's on the exam before we start making material. So we did everything we could using the OCG and using all of the other materials Cisco puts out there. Of course, most importantly, just the exam blueprint itself, because Cisco tells us what's on the exam. We just need to train on it and study it. And overall, I'd say we're not making plans to go back and add anything to it based on my experience, the experience of the other trainers. There are definitely things on that exam that were difficult. Little nuances and corner case scenarios and things like that I wouldn't expect a training course to necessarily cover without being like, hey, they're going to ask this question on the exam, so you better go study it. We definitely don't want to cross into that territory either. That would not be good for anybody. But, just to kind of offer some thoughts on the exam. So first and foremost, like I said already, it is a difficult exam. I did pass it, but you need an 825. I got an 825. Okay, that's how much I passed it by. I passed it by a margin of 0. So it was it is an exam. I'll tell you what, from my perspective, where I struggled were two areas. First of all, just the nitty-gritty syntax. So knowing exactly how things are configured, because I spend a lot more time at a whiteboard than I do at the command line, and that's on me for not properly studying for this exam. If I were to go back and do it again, I would have spent more time at the CLI to make sure that I understood all of the syntax of all of the concepts that we talk about regularly, not only in the study group, but at CBT Nuggets for the ENCOR course. The other thing that I definitely could have used more work on was network automation. That is on the blueprint. It is fair game, and I got hit pretty hard on it. I'm not gonna lie. That is a weak area of mine. I'm not 100% on every single concept within the ENCOR world. Programmability, network programmability is definitely a challenge for me because it's just something I've not done as a job. Before I was doing all network designs and network deployments and things like that, but by the time I moved into this role, network automation was really starting to take off, and I had yet to really see it myself personally before coming to CBT Nuggets. So spending more time with Knox Hutchinson and his, not only the ENCOR portion of the automation section of ENCOR, that was great. But in hindsight, I really should have sat all of the DevNet as well, just to make sure everything is covered. But there's no magic formula for passing the ENCOR. I would never recommend that you study only CBT Nuggets content and then go take the exam. In the same way, I would never recommend you only study the official cert guide or you only study one of the other vendors out there that makes training materials. Having usually at least two sources of study material is going to help the most. And then beyond that, hopefully, maybe even having a third, honestly, if you're going to have a third one, that would be what this ENCOR study group is all about. My hope for this group is that as you're going out and you're studying for the ENCOR, you might find a gap that maybe CBT and the official cert guide gloss over, and you're like, why did you guys gloss over this? Help me out. Help me understand how this works. And, we in the study group might be like, hey, that's not even on the blueprint. Don't stress it. Or at least we could hopefully respond and say, well, here's how that works. So just to kind of lay some expectations out there. Like this week, we are studying the hierarchical network model. And so it's a design-oriented conversation. That's great. But I tell you what, not everybody who's studying, in fact, I'd expect very few of you happen to be in this chapter right this week. And you just happens to align perfectly. If that's the case, that's great, but you won't be aligned with us next week, right? I mean, the odds of you needing to or being in the exact same chapter as where we are, is slim to none. But what we can do is, number one, by covering the hierarchical network model, allow you to come in and get refreshed and ask any questions that you might have. But the second thing, too, is don't hesitate to bring another question if you happen to have that. Like, hey, I'm studying spanning tree. I don't understand the concept of root guard or UDLD or loop guard or something along those lines. And obviously I can't answer it live since this is pre-recorded, but I am sitting here in the chat with you answering questions as best I can. So ideally we are coming together as a group and just answering those questions and enabling you as you're studying for the ENCOR or for anything that is related to ENCOR. So moving on here, let's take a look at our agenda. So today we're talking about, like I said, the hierarchical network model and what exactly that looks like. This is this building block concept when it comes to network designs, and we're going to be talking about that, the campus architecture. I can say it, really I can. Which does consist of that core distribution access. Now, it doesn't look like much is on the agenda, but as some of you know, there's a lot to these concepts, and we're going to make sure we spend our due diligence covering all of these individual concepts. So a little bit of background for those who don't know me very well. I've spent most of my career working for a Cisco partner. So what that means is let's just back up. When I first went to work for this partner outside of college, I graduated from college. And so, of course, new kid out of college, what am I doing? I'm going and I'm physically installing racks for the senior network engineers. And I'm plugging cables in. And my favorite thing, and the thing I did the most, was climbing up on ladders and installing wireless access points. Soon I started configuring those wireless access points and wireless LAN controllers. And then I started configuring switches and such. And then I took a different job for a medical clinic, worked for a couple of years there, and then I came back to that Cisco partner, but at that point I had gotten my CCIE while I was away. And so now I landed with the Cisco partner as a CCIE, and now I'm doing design work and I'm doing install work. And over the course of, I'd say, the last 5 years or so, my work steadily shifted from out in the field doing the installs to really doing what I'm doing here with you. I would go to customers and I would whiteboard. I would grab a whiteboard, do markers, say, hey, this is exactly why you'd want to go with this solution that we have, and this is how we do the configuration. And I spent more time in front of customers doing the whiteboarding than I would doing the actual CLI, which is probably in hindsight why I am a little rusty on some of my syntax trying to take that ENCOR exam. So design, when it comes to design, I love design. I have spent a lot of time over the last 5 years in network architecture and network design. And it was asked last week, I think I mentioned some of my passion for design last week, and somebody in the chat asked if I'd ever go after my CCDE. And I did sit the CCDE written once, probably about 4 years ago at Cisco Live. It was the free exam. I was like, I didn't do any studying. I just decided to go in and take the CCDE, written, not the lab. And it was very service provider heavy. You needed to know MPLS in depth, IP version 6 in depth, multi-protocol BGP in depth. And I just really felt like, that's not where I'm playing at the moment. But so anybody who's thinking about taking CCDE, just know that it is very route switch and service provider focused. So at the time I was more data center focused, and I thought, as much as I love design, let's just kind of roll with I guess data center stuff. So all that to say, maybe one day CCDE, because I just, design is fun. It should be fun. It's basically, what we as engineers like to do. Yes, we like to solve problems via the command line. I love bringing up a successful OSPF connection, right? It's like, yes, we're exchanging routes, and there's just that, that feels good to bring that in, a little bit of euphoria there. But design is kind of the same way, because we're taking pieces of a puzzle and arranging them. And there's so much almost artwork involved with, because there's subjective decisions that need to be made. For example, do I go with a series of stackable switches, or do I go with chassis switches? There's very rarely a black and white answer. Like, sorry, but you're always going to go stackables in this scenario. You're always going to go chassis in this scenario. So some of us as engineers, we're not as comfortable with gray conversations like, okay, we could go this way or that way, and which way's maybe a little bit better, and it's subjective, and we're not as good with those conversations natively or naturally. At least a lot of us aren't. And so to get comfortable with that can be a little bit of a challenge, and I get that. But don't fear it. This is, for many of us, going after the ENCOR is going to be the first real step into network design. Up until now, Cisco has wanted us to learn how to do a show version. Those are bad examples. An access list configuration. For CCNA, those who have passed the CCNA, you've learned a lot about how to configure things at the CLI, and that's great. But at some point, we do need to understand how these networks fit together. And it's not a technical conversation, not a technical CLI level conversation. This is a technical, like, how the building blocks all fit together, how we're going to connect these things to one another, and what makes a clean design versus a complicated, messy design. There are some really good architectural design models, one of which we're going to talk about today, that will help us determine the best way to build networks. And once we know how to build networks, even if we don't spend our time doing network design day to day, if your job is to keep a network online and that's really your job and you're at the CLI every day, a conversation around design is only going to help you to be able to troubleshoot issues that are arising and potentially identify ways that maybe our network could be a little bit better. So definitely don't shy away from the design conversation. All right, so moving on. Let's get to some actual conversation. I know everybody's, you're all like, all right, let's do this. Let's get it. We're fired up. Let's do some network design chats. So, why do we have these network models? What is the hierarchical network model? The hierarchical network model, it does to networks what we kind of did with programming 15, 20, probably longer years ago. This concept of object-oriented design. When from a programming perspective, you used to just make like maybe one long series of code, one long, what's the word I'm looking for? Script, I suppose. It would just run everything all the way down. And then we learned this concept of object-oriented code, like C++ was a little bit more of an object-oriented coding language than C was. And the idea was this: you would package up code in an object, and you'd be able to reuse the code that you use in that object. But not only that, but you'd be able to inherit, properties from that. And so we might not look exactly alike when we copy and paste it around and such. When we looked at networks, let's just draw some of this out. When we were first growing our networks organically, this is the kind of thing that would develop. We'd have a bunch of users who are hanging off of a bunch of switches, and then all of a sudden we have users down here that need to connect to a switch, and there's no good way to attach these users to any of the upstream switches. And so what do? We throw a network switch out there, or maybe it was even a hub back in the day, and you'd connect that up to the rest of the network. And hopefully we're running spanning tree so that there's no network loops. If it was hubs, then good luck. Hope somebody doesn't just loop your network, right? And so you'd grow these networks organically as you need switches in various places. And this is well and good, except now, all right, well, we just got access to the internet, right? We're going to bring our internet access into this switch up here, and we're going to need some servers. And so, just 2 or 3 servers, that's it. So we're going to throw these servers down here, connected to that switch. So now we've got users connecting to that switch. We've got servers connecting to that switch. And, we just found out we need another server, but there's no room in that closet. So we're going to throw that server up here. And this is probably giving some of you a panic attack already. The thought of trying to manage this network is, it's just a nightmare-inducing thought. And so instead, what we need is a model that tells us how exactly the best way is to build this thing out. Think of this model as that early concept of programming where we just kind of list everything out. All right, we need building blocks. We need an idea that would allow us to kind of modularly arrange our network a little bit better than what we have going on here. So let me flip over to a new fresh board. That's not the right thing. Okay, I'm not doing this very well. There we go. Turn that layer off. All right, so this is what the hierarchical network model is all about. We are going to reduce every portion of the network, every part of the network, into a different block. So let's just start off with this idea of a core block. If we have a core block in the middle of our network, that block could consist of 2 switches, 3 switches, a bunch of routers. Depends on the network at play. In a lot of cases, it's going to be 2 multi-layer switches, kind of talking layer 3 when it comes to core blocks. But the idea here is this. I've got my core block here, and I can hang all of my other network blocks off of this core block. In a lot of cases, our networks are built to look like a hub and spoke topology, a hub being, the core block being the hub, and all the other portions of our network, the other network locations, would be the spokes. And so those different spokes are going to be different blocks in the network. So what are some network locations that we can think of? So we mentioned having the internet. That could be its own block, the internet block. That would come in. That would be its own set of routers and switches and such. Whatever's making the internet work. Maybe even some firewalls are in there. And then we mentioned servers. Well, that could be a data center. One thing we didn't talk about is the fact that we might have a second site or a third site or 80 sites all coming in via the wide area network or the WAN. So that would be the WAN block. So all of our branches are going to come in via some switches and routers that are inside that WAN block. And then what we think of a lot of times is the classic core distribution and access layer. Now, core distribution and access layer, absolutely a thing, but usually that core distribution access concept is within a single site. So if I'm going to have my core switches, which I have drawn here, the core block right there in the middle, and then I have my headquarters. Let's say my core is located physically in my headquarters. Well, I'm going to have a distribution block hanging off of the core block, and then I'm going to have access switches hanging off of that. And we'll get into the details of what all of these blocks mean, really. Distribution access especially as we move forward here today. But what if I have another building that's coming into the core via fiber, let's say? It's not coming in through this WAN connection. That's like T1, T3s, MPLS circuits potentially. But maybe I'm a campus environment. Maybe I've got another, like 2 buildings. Maybe I've got 15 buildings. Regardless, I've got other buildings that have distribution switches and access switches. And so what I'm going to do is I'm just going to keep bringing in those buildings. So now I've got a distribution with an access switch or access block hanging off of it. That would be building 1. Change colors here. Make that a little clearer. So we've got building 1 here. Technically, we've said that the core block is in there, but we'll just leave it like that for now. And then we have building 2 here. And if I built the network like this and that's where it ends, fine. But what if all of a sudden my business is so good we build a 3rd building? Well, in the organic scenario, we're throwing switches around and we're just ending up with this mess of a network. And so this new building is not only going to require a new network in the building, but it's going to bring its own servers. It's going to maybe require a redundant internet circuit of all these things. Just how do we bring that into this network? Well, the building block, the hierarchical network model, kind of gives us that answer, because all we're going to do is we're going to bring that new distribution block into the core in the same way we did the other ones. And if I need to throw some new servers into the data center over here, I can do that. If I need to throw another internet circuit in, I can do that there. If I need my own internet circuit, then at least I can figure out how exactly it's going to look. I would have an access switch hanging off of it there, and I would probably just bring an internet circuit right into that distribution layer. I don't even need an internet block out there. And what this allows me to do is just to continue to scale out my network far and wide, because again, we can look at this model and say, what if I want a second data center? Well, right there, second data center, there we go. What if I want more buildings, more distribution blocks? What if I need more WAN circuits? Well, all those WAN circuits are going to keep coming into the WAN block, so I just need to create new WAN routers, maybe beef up the routers that are in there, deploy new ones, etc. But my network architecture doesn't change just because I brought in new WAN circuits. Again, think back to the cobbled together version. If I bring new WAN circuits in, I mean, I'm going to fit them, plug them in where I can fit them. Or physically where they go is where I'm going to plug them in, whatever device is closest. And it doesn't lend itself towards a proper way of allowing us to troubleshoot the problems that arise. We bring new staff on. It's hard to explain where everything is. Like the network person who's been there forever, they know exactly where everything is, but maybe they quit or retire, and now you bring in a new person in, and they're trying to figure out everything of where it all is. And so this is not only good from a technical perspective, troubleshooting issues, knowing where the network boundaries are, etc. It's good for a human to be able to walk into this type of network relative to the other type of network that we demonstrated. So what does this block to block connection look like? Because when I look at a block, I mean, is that one switch? Is it two switches? I already kind of mentioned that it could be multiple switches, multiple routers, etc. But what about these connections? Because it just looks like they're all single connections. Well, if we're going to have let's say a core block, let me just do it like this. Make it a little bigger. Let's say this is my core block, and I want to connect it to my distribution block. Well, typically, in a lot of cases, each block is going to be represented by two switches. The biggest exception of that would be our access layer down here. Access layers are probably going to be a lot of switches. However many switches we need to connect all of our users. It could be 30 switches. Who knows? We'll get into distribution access layer here in a little bit. But if I'm going to connect two of these blocks together, a lot of times what I'm going to do is I'm going to take the two switches that are in one layer, two switches that are in the other layer, and I'm going to bring all of these together in a full mesh of connectivity. So I'm going to do the bow tie thing we like to make sure that the switches themselves are connected to each other. And this here is all layer 3. And I know my face covers up part of that. That says, I'll just write it over here. That says distribution. Sorry about that. All right. So that's all layer 3. All of that connectivity is layer 3, which is why this scales so well. We don't want to push layer 2 everywhere. We don't need layer 2 between my headquarters and my manufacturing building across the way. Let's just do layer 3 there. And one of the ways that we're going to help maintain that over time is to, again, have that dedicated data center space, because a lot of our layer 2 requirements happen between servers. So all of our servers are in the same spot. They can all be on layer 2 there, and we don't need to push layer 2 out to the rest of the network. So layer 3 gives us a lot of scalability. If you're not familiar with that concept, it simply comes down to reining in the broadcast domains, reining in your spanning tree domain, making it so that we can have new subnets at every location. The biggest downside to a layer 3 network is the inability to share subnets and broadcast domains between locations. But again, there's almost never a reason why building 2 would have to be on the same subnet as building 1. I mean, most applications we're going to push out today are able to talk across layer 3 boundaries. You might have the occasional, what I've seen, for example, would be wireless devices that have to be all on the same subnet and people roam between two buildings. That is a challenge. We can get around that nowadays with tunneled wireless protocols like CAP-WAP going through wireless LAN controllers and such. But without that, that's a challenge. If you have to be on the same subnet between two locations, you have no choice but to push layer 2 to those different locations. Otherwise, push layer 3 everywhere. That's really what we want to accomplish. A layer 3 network is infinitely more scalable. Slightly exaggerating on that, but basically infinitely more scalable than a layer 2 domain. So, we're going to talk a little bit more next week, I think. We'll have time to get into Cisco software-defined access, or the Cisco's Fabric the name of the word is escaping me right now, but there's their software-defined access fabric, or campus fabric. That's what it was. The campus fabric concept, which pushes layer 3 everywhere and then puts layer 2 over the top from a tunneling perspective. That's really a best of both worlds approach. It's why it's a very popular architecture that's getting deployed to a lot of places right now. But it's living that software-defined dream, which really gives us the ability to put whatever we want, wherever we want. But outside of software-defined networking, our physical architecture matters. And if I physically have my distribution switch connecting to my core switch like that, well, then I need to configure it appropriately. And so here on the right, this is the way we do it. Incidentally, by the way, once we move to software-defined networking, campus fabric, software-defined access, all these buzzwords and buzz acronyms, I could just keep throwing them out at you and we'd all quit because it sounds awful. All these acronyms, new acronyms that are coming out, we just like to say them. The new way of doing it is going to really require us to do a lot of layer 3 everywhere. So the more layer 3 we can do, the more it will prepare us for deploying a campus fabric. All right. I think the only other thing I didn't mention, I was checking my notes here, from a building block perspective, the only other block you might see commonly used would be a network services block. So network services would be things like potentially your firewalls, an application load balancer, a WAN acceleration engine, like those kinds of devices in large enterprises will be deployed to their own separate sets of switches. And when you're deploying it to its own set of switches, you might as well layer 3 connect that. And if you're going to layer 3 connect that, put it through the core, at that point it's its own network block, which is why these blocks show up. But in most cases, I'll say in my experience, most cases we don't usually, with great intention, put all of our network services out in their own block. If you're a shop that's like, well, I've got a wireless LAN controller and I've got a firewall and I've got, maybe 4 or 5 of these devices, just put them where they maybe make more sense. Wireless LAN controllers probably should go in distribution layers where they can. Firewalls should probably go in the internet block. That would be fine. We've got places for these other devices if needed. But if the scale is so large that they require their own network infrastructure, that's when it becomes its own block. Okay? But yeah, for the most part, these are the blocks. It really is going to be the WAN block, the internet block, the data center, and potentially network services. And then from there, it's just distribution and access blocks. So at this point, what I want to do is just kind of go into the campus architecture, which the campus architecture is this traditional classic core distribution and access model. So let's go ahead and dive into that. I need to clear my board here. What are we doing here? All right. I got my iced coffee keeping me going here on a pretty warm day. Pretty warm and humid. Probably should have cranked down the temperature before I came into my office here, but I'm getting warm. All right. So, campus architecture. Campus architecture, in a way, it started the hierarchical network model, because when in the era where we're just kind of connecting everything together, the idea that we came up with was to have this concept of a core and a distribution and access layer. And that was the extent of it. It was just bring all of your network devices together. We're going to put all of the, let's say, the WAN circuits and the internet circuits and the servers in the core layer, and the distribution layer is going to be kind of the physical interim. It reaches out to all the access switches, and that was basically it. But as we've expanded our network design and figured out what works best, this is where it leads to the hierarchical network model. That said, we're not done with core distribution and access. This is still how we build a campus architecture. A campus architecture would just usually equate to a building. It might be a series of buildings because we might have multiple distribution layers, as we just alluded to in the previous screen. But here's what this looks like. So we know already that the core is going to bring the rest of the network in. We just talked about that. In the modern network, the core of the network is not the end of the network. It's actually the middle, right in the center. If I want to get anywhere else in the network, I should first send my traffic to the core, and the core will then send it out whichever direction it needs to go. So that's well and good. What's going on? We're going to skip over the distribution layer. So what's going on with this access layer? What really is the deal with our access layer? What's going on there? So the access layer is where we where we connect all of our end devices. These end devices could be laptops. They could be access points, which is kind of like an end device, but also kind of like a network device. So, but it's still, it connects in via the access layer switches. It could be, so in that sense, we've got wireless clients hanging off of it. IP phones, by the way. IP phones are absolutely part of the access layer. What else do I have on here? Oh yeah, cameras, right? We've got pan, tilt, and zoom cameras. Oh, either way, we've got cameras. We've got video conferencing systems. We've got all kinds of things. This is the reason why we have a network, is so we can connect our end devices to it. But the last thing we want is to start connecting things up to distribution switches and core switches and wherever we want. And we've probably all seen networks like that. I mean, I know I have. We walk into a network that you could tell was designed to be core distribution access, and yet you've got all kinds of user connections coming into the distribution layer, maybe even the core layer. Say, okay, well that was good that we have this distribution layer, but it would be best if we kept all of the end devices pushed out towards the network access layer. That's the point of the access layer. Now, something I know that Cisco likes us to know is this idea of like, what services do we see at this particular layer, all of these layers, and we'll talk about all of them. At access layer, one thing we're going to see a lot of is Vlan assignment. Okay, this is very important. This is why we see switch port access VLAN commands on access layer switches. The VLAN as the traffic comes into the network, into the access layer switch, it is not tagged. I mean, my PC isn't tagging its own traffic. I could download a software or firmware package from a network card and probably tag my own traffic, but for the most part, that's not going to happen a whole lot. Phones will tag their own traffic, and this is where we need to decide if we're going to trust the downstream device or not. But speaking of which, not only the VLAN, but this is a big one, Qos Marking. Okay, quality of service has a lot of different components to it. We have marking, we have shaping, we have policing, we have queuing, buffering, all kinds of QoS notions here. But the marking is just like what I described with the VLANs. It's the exact same concept where as traffic comes in, it is untagged, and we as the network admins, we get to decide whether we're going to tag that traffic and whether that traffic is actually going to be marked at all, or if it's marked, then what we're going to mark it with. We're going to mark it with a high priority or a low priority. And so this QoS marking concept happens at the access layer switch. We want to mark traffic as close to the edge of the network as possible. We're going to see that not just with QoS, we already mentioned VLANs, but even security. You know, these days we have this concept of scalable group tags or security group tags, SGTs. And SGTs would also get marked at the access layer as close to the access layer as possible. Because if I mark something down here and then I send it upstream, well, then I can enforce that policy as part of that traffic communication. But if I don't mark it, there we go. If I don't mark it there, if I mark it up here at like the distribution layer as that traffic comes in, well, now I'm sending traffic, and this part of the traffic, this component, is not being enforced according to my policies, whether it's security or just quality of service or what have you. So we want to mark as close to the edge as possible. And in a lot of cases, we want to enforce as close to the edge as possible. All right, I thought my pen broke there, but we're good. So anyways, so that's just a concept there. What else we got here? Okay, so trust boundary too. So I mentioned QoS marking. This is related. Trust boundary. I mentioned it already. This phone is attached to the network, and it's telling me that I have it's telling me that it has a QoS value of 5. I keep thinking of the different ways of wording that, but it's tagging its traffic with a COS or a QoS value of 5. And I need to decide, because 5 is a pretty high number, and that's exactly what Cisco Voice is designed to market as. So it's doing its job, but I have to decide whether I trust it or not. For example, I might have a PC that connects in via that access layer, and it starts tagging its Netflix traffic with a QoS value of 5. That's not great. I don't want my Netflix traffic, my video streaming from the internet, going into the same queues as my voice and video traffic. That is, I mean, it's our job as network admins to lock down on that and make sure that that's not happening. And so we put this concept of trust in place where we're not going to trust anything, any port by default, but we're going to pick the ports where we trust. And Cisco gives us some macros and some shortcuts for that. For example, we can trust Cisco phone. So if it detects a phone via CDP, it'll trust it. If it doesn't see that it's a Cisco phone or a Cisco telepresence unit, then it will not trust it. And so as people are coming now, I can only tag the traffic I'm sending. I can't tag the traffic I'm receiving. So the Netflix example is actually a bad example. But what if I have a music server or something like that? It's on there. It's sending a stream to my network and tagging itself with a value of 5. That would be bad. Yeah, I guess I can't force Netflix to use a particular QoS value as a bad example. Some other things. So I mentioned security group tags. What about other security mechanisms? So we've actually got concepts such as port security. Port security says I can only have X number of devices on this port. And so in most cases, I'm wanting to lock it down to 1. I only want one device, one MAC address out this port. So I can lock it down to 1 at a time. That helps with somebody bringing their own network switch in, or heaven forbid, a hub, plugging in at their desk. And now all of a sudden I've got 15 different MAC addresses showing up. So that helps with that situation. And also I can lock it down to a specific MAC address. So from a security perspective, if I've got a public space and I want to provide a phone into that public space, well, now that phone has a network connection. If I'm a malicious bad guy, I could go into that public space, sit down with my laptop, unplug that phone, and plug the port into my laptop. And now, whereas I might have only had guest access via the wireless, all of a sudden I'm on your wired network just because you left a phone out that was supposed to be a convenience for everybody. And I'm taking advantage of it because I'm a bad guy. It's what I do. Well, that port security can say, hey, wait a second, I'm only allowing this one MAC address on this interface. And so since you lost, I lost access to that MAC address and your MAC address is different, well, I'm not going to trust that anymore. So it will block that traffic. It will not allow that bad guy to get through. Heavens, I remember in college back in the early 2000s, we'll say, and I had just gone out and video game systems had just gotten online. I got an Xbox, not 360, not Xbox One, but just Xbox. And it had a network port on it, and it could actually connect. Had a couple of video games you could play online at the time. Again, brand spanking new for a video game console at least. And I remember unplugging my PC and plugging my Xbox in thinking that would work. And lo and behold, my Xbox would not work. And I had to call up my IT at the university, say, hey, how do I get this Xbox online? And the weird thing is back then they like to control things a lot more, like, oh, we don't allow video games systems on our network. It's for educational purposes only. Like, you imagine that flying today, telling a college student, oh, sorry, we don't support video game systems on our network, right? So I did what every other industrious, college student, I was going to say, something about learning, network student. I wasn't a network student. I wasn't there to study networking. I just wanted to play my video games online. And so I found a way to clone my MAC address of my PC onto my Xbox and get around it. So that would be the downside to port security is it should not be your only security mechanism, because a bad guy is going to be able to potentially clone the MAC address of whatever device they just unplugged. But it's still, obviously, it can still go a long way towards helping us to lock down things, make it more difficult so that a bored teenager who happens to be hanging out in that public space isn't necessarily going to be able to do anything because they're not setting out to trying to hack you. They're just trying to mess with you a little bit. All right, and last but not least with this access layer, we need to decide this connection. Should this be layer 2 or should this be layer 3? And this conversation, we're going to have a lot more to say about this next week. So come back, or I say next week. I guess I should try to advertise several times throughout this. We are doing this every other week, just to kind of start off and see how things are every other week. So that'll be in 2 weeks. So today is, what is today? July 1st. Today's July 1st. July 15th will be the next study group. And we're going to cover the enterprise network design, which, even though it feels like we're talking about network design, we're really just covering the model. And then next week, we're going to cover our options for how we design all of these things. And so one of those options is, do we connect this access layer via layer 2 or layer 3? And we already talked about some of those concepts, but we'll drill into more detail next week. Okay, so that's it for the access layer. The way this works, let's kind of draw this out here on the right. So I want to have it physically drawn out on the right. So when we have a building with switches, a lot of times with users throughout the building, a lot of times what we end up with are the users. The users are everywhere, right? I mean, physically, like they're just somewhere in that corner of the building, somewhere in that corner, some are on floor 2, floor 3, floor 4, maybe even higher, depending on the type of building we're in. It could be I've been in a lot of warehouses where the warehouses themselves are so big, you can't even run Ethernet that far. So you have no choice but to run fiber from one end of the building to the other and to throw some switches out there. And we just make do while trying to abide by this model concept. So what this looks like physically is a bunch of access switches throughout the building. Now, usually what we're going to do is we're going to end up with a series of network closets. So we're going to have these network closets. Each network closet is going to have so many switches in it. Best practice is probably in the 5 to 7 range, but you could go, Cisco supports stackable switches of up to 8. It used to be 9, now all the new models are 8. And but then they've got chassis as well that can go, I know there was a 4510 at 8, so at least up to 8 different blades. I know the 6513 used to go more, but they don't make that one anymore. So however many switches or chassis blades we deploy, either way, this is going to be one closet. And our users are going to attach down here. I went right underneath myself, didn't I, again? Lovely. All right, let me... Come on, erase. There we go. All right, so I'll just draw this a little higher to get around my face. I really need a reminder on my screen not to draw under my face. All right, there we go. So we've got a couple of closets, and we're deploying, maybe it's chassis switches, maybe it's stackable switches. That's a whole other conversation. Do we deploy chassis switch? Do we deploy stackable switches? The stackable versus chassis conversation wasn't really my plan to go into this, but I'll at least drop a couple of things. Chassis are nice in that they're very simple. Okay, like upgrading software on a chassis switch, really easy. Sliding a new switch into the chassis or new switch blade into the chassis, really easy. The scary thing about a chassis is that you can run out of space. And also, if you only need 2 or 3 switches in your network closet, they can be a little more expensive than just throwing 2 or 3 access stackable switches out there. Whereas stackable switches, way more flexible, can go whatever size you want, 1 switch all the way up to 8 again. Usually have good options for fiber connectivity. You do as well with the chassis. A lot of times fiber connections on chassis switches will be more expensive. So, but they're not nearly as simple to manage. There can be issues with software upgrades. There can be issues with just troubleshooting issues. And so they're far from a chintzy design. I personally love stackable switches. But it's just sort of, this is where you almost have to pick your poison. Like, neither design is perfect, but you absolutely want to go with one of these. I mean, because the last thing you want to do is daisy chain switches in your access closets like we did back in the 90s and 2000s. So now we've got these two technologies that really help us out. I mean, chassis switch, they've both been around forever, right? But the technology, especially for stackable switches, has really over the last 10 years become more accessible down at the layer 2, or the access layer. They didn't used to be there. This greatly simplifies our spanning tree environment because of how we're going to end up connecting these up to the distribution layer. So let's go ahead and flip back over here to the left and look at this distribution layer. So what's this distribution layer all about? The distribution layer, two things. Physically and logically we need to talk about. So physically, the access layer I mentioned earlier is going to have a lot of switches. We could have, I don't know, I mean, we could truly have dozens. I don't know that I could go so far as to say hundreds of switches, but technically we could, as long as we have the port capacity and the performance needs at the distribution layer. Because what we're going to do is, let's say we have 30 network switches, or 30 network, I thought I said switches, I'm immediately thinking is that chassis switches or stackable switches, but either way, like 30 stacks or 30 chassis out there. Definitely doable. And each one of those is coming back to the distribution layer. Well, obviously, we need physical ports for that. And so these distribution switches are typically going to be chassis. I would say a lot of them are chassis. You can usually get more performance out of chassis switches, or at least you could. These days, stackables are pretty darn good too, so don't get me wrong there. But either way, we're going to have physical ports connecting all of these devices. So if we have 30 devices, I mean, we're going to have 30 connections coming into the distribution layer. And usually we have, again, as with the core switch, we're going to have 2 switches in that distribution layer. So over here on the right, let me just switch colors. I should have switched colors before this. Over here on the right, let's say we have 2 distribution switches. These distribution switches, by the way, these could be teeny tiny. Even if you've got 30 switches that you're bringing in from a connectivity perspective, a 1 rack unit server has 48 ports. And so if we've got 48 ports here and 48 ports here, and I've got 30 network closets all coming in here, 1, 2, and then again, I've got to watch my face, 3, 4, 5, 6, 7, 8, 9, 10, 30. I've got 30 ports on this switch consumed, and I've got 30 on this switch consumed. So these distribution switches can be small. They do not have to be big, beefy switches. Now, we need to make sure from a packets perspective, or packets per second, and a bandwidth perspective, we need to make sure that we're good there. MAC address counts, etc. But we need the physical ports in order to terminate all of our access layer connections. Now, as mentioned, these could be layer 2 or layer 3 connections downstream, but upstream, in most cases, we're going to be connecting to the core via layer 3. So these do need to be layer 3 switches, or capable of that, so multi-layer switch would be ideal in this scenario. So the distribution switches, let's see here. So what services are we running? Let me switch over to green for services. What services are we running at the distribution layer? Well, the services we're running, first of all, one of the first things we might think about are VLAN interfaces. So we call those switch virtual interfaces, or SVIs. So we've got SVIs running at the distribution layer. Now, this is true if it's a layer 2. If this is layer 2 to the distribution layer, then we're going to have our SVIs. If we're not layer 2, then those SVIs have to live actually downstream on the access switches. Now, most networks are going to run layer 2 to the distribution layer, so that's where our SVIs are going to be seen in a lot of cases. For the most part, if we're running layer 3 to the distribution layer, remember, we just talked about physical ports, now we're talking about logical services that the distribution layer provides. If we're running layer 3 to the edge, for the most part, all of those services are at the edge. And so when it comes to the distribution layer, it's all about the physical side. It's all about just making sure I've got the port density. I just need to connect all of these layer 3 connections together and hand all that off to the core, and that's pretty much my lot in life if I'm a distribution layer connecting to a layer 3 access layer. All right, but in most cases, it's not layer 2. It's not layer 3. It is layer 2. And so in that case, we need our VLAN interfaces to live at the distribution layer. We're also running on those SVIs our first hop redundancy protocols. We'll be talking about that, I believe, at the end of the month. Yeah, I'm looking at my schedule now. Tentatively for July 29th, we'll be covering first hop redundancy protocols and other high availability techniques. So this would be HSRP and VRRP and GLBP. Those are really. I mean, it's the three different first hop redundancy protocols. And so the idea there is that my default gateway is the SVI. So my PC here, that is a wacky PC, but there we go. Wacky PC has a gateway configured and it's pointing to that SVI. Well, if that SVI were to go down, because I'm pointing to the SVI on this switch here on the left, and this whole switch goes down, I need to be able to get back online very quickly. And so I have an SVI over here that is managed via one of these first hop redundancy protocols. And because the first hop redundancy protocol is running, it very quickly brings it online, and the users are none the wiser that that switch even went down. So it's great that we have a path around that switch that died, but if all the users in the network can't access the default gateway, then there was no reason in the world to have redundant switches. Because if my primary switch goes down, I'm largely out of luck. I guess I'll eat my words a little bit. There's no reason to have it. You can always manually bring it up, but that's a very slow process. So anyways, so our first hop redundancy protocols are absolutely a part of and the SVIs are part of the distribution layer. It's usually where they're deployed. That's the word I'm looking for. All right. What else? Routing. Okay. So routing neighborship. So yes, as mentioned, we have a layer 3 connection up to the core. So a lot of times we'll say that we have routing protocols running at the distribution layer. Now routing protocols, like Cisco says, routing protocols run at the distribution layer. I don't like saying that because routing protocols run everywhere. But I think what they're saying is that this is where routes really get injected into the routing protocol. Because in a network, when I have a core here in the middle and I've got a bunch of nodes around the core, really what we're doing is we're all advertising our routes into the core, and all the core is doing is passing those routes to the rest of the network. Yes, the core switches are running the same routing protocols. They have to. But the reality is that we're forming neighborships with the core and injecting. We're doing all the injections. And so this is also, by the way, where we're going to see not only routing protocols, but also routing summarization. So I might decide that, okay, I've got, I don't know, let's say I have 50 VLANs in this environment. Well, that's 50 different subnets in that environment, and maybe it's 10.1.0.0 through 10.50.0.0. Well, I can summarize that pretty well. I didn't pick pretty numbers for summarization. I should have gone like 0 to 32, 31 or something like that. But either way, I can advertise that as a group. And I might even just say, you know what, 10.0.0.0, again, bad example because it's a little too large, but I could say, hey, just send the entire /8 to me. You know, that's a network summarization. And there's no real reason to run that in your network core. You could do it, but for the most part, that summarization is going to happen where you're advertising the routes. And so this is where we oftentimes see network summarization done. We are getting pretty low on time here, which is good because we're about to wrap up. So the last thing is, again, I mentioned security here. Guess what? Security at the distribution layer. So a lot of times we're going to see access control lists at the distribution layer. You can deploy them to the access layer. I mentioned earlier you want to deploy that as close to the edge as possible. The problem with that is you have to find the balance between as close to the edge as possible and also not deploying it to 2,000 network ports. This is where the era of network automation is really coming into handy because a computer doesn't care. If I have to push an access list out to 2,000 network ports, I don't care. But me as a human, not only deploying them, but managing them and maintaining them over time. Imagine if I don't know, I had to change a security setting in the access control list. Well, now I have to touch every single switch in order to make that happen. Not all 2,000 ports, fortunately, but every single switch in the network. This is where network automation really saves our bacon as network admins, because, hey, maybe it's easier for me to deploy a network security policy into my distribution layer because there's only 2 switches. But it would really be better if I push that policy out to all my access layer switches. And so this is why, again, network automation can help us do the things that we really should be doing, but just aren't tenable. They're just not doable for us to go through that much pain and turmoil in order to deploy a proper policy. Okay, so the security, though, I mean, realistically, we're going to see a lot of access lists, because access lists like to be deployed, because they're sentient beings, right? But they do like to be deployed to access control, or that's what I just said. Access control lists like to be deployed to SVIs. There. So the SVIs are at the distribution layer, and therefore that's where a lot of access lists are going to go. QoS, there is going to be QoS enforcement. We might police the QoS before it gets up to the core. That would be dropping traffic versus, we might also shape. We might also do some traffic shaping. A lot of that's traffic shaping and policing will be done at the WAN block and the internet block, though. And so in a lot of cases, we're not going to do a lot of QoS manipulation at the distribution layer, but we certainly could. Last but not least is the core. All right, our diagram's getting pretty busy here, so it's good timing. What is the core concerned with? Now, I don't know about you, but when I was learning network design and I was learning all of this stuff, I would have thought that the core had the biggest, baddest switches, and I would have thought that the core had the biggest set of protocols running. Like, it's the core. It's everything. If it goes down, the whole network goes down, right? And technically that's true. But the network core is concerned with really one thing only. And if we go back to our previous drawing, which is kind of tricky with my whiteboarding app here, let's just try this. Yeah, okay. In fact, there. We'll do it like this. Looking at this diagram, you might be able to figure out what is the core primarily concerned with. What's the one thing that it needs to do? Switch traffic. Its entire goal is to get... oops, I'm on a bad layer now. There. Its entire goal is to get traffic from this block to that block, and from this block to that block, and from this block to this block, and that block to that block. That's primarily what it cares about. Fast layer 3 switching is what Cisco says. And so we want a switch that's capable of high packets per second. And a switch that, just like the distribution layer, we've got to have physical ports, but a whole lot less, because even though we might have 30 access switches down in the access layer, we're not going to have 30 data centers. In a college campus or a large enterprise campus, you might have a lot of distribution layers, so that's certainly possible. But at the same time, we're less concerned with this. So a lot of core switches can be a Catalyst 9500, for example. Technically the 6800s, like the big, strong chassis switches that Cisco makes, those are built to be core switches. Don't get me wrong. But at the same time, if we can accomplish what we need to accomplish on a smaller set of hardware, there's nothing saying we have to build our network core on the beefiest switches that we can possibly deploy. The core doesn't do that much. From a protocol perspective, we already talked about SVIs. Well, there are no SVIs in the data center. We're not running FHRPs. We shouldn't be doing access list blocking because we don't want the core to be focused on that. And once the traffic gets to the core, we already said we want to block as close to the edge as possible. So if we're not blocking at the access layer, we should be blocking at the distribution layer. Everything that gets to the network core should be good traffic at that point. What else did we talk about? QoS tagging, port security, Vlan assignment. All of these things have already been done. All we have to do as the core is to say, you're coming in, I'm looking at your destination IP address, I look it up in my table, I figure out the outgoing port, and I send it on. That is my role as the core, and that is why we only had to spend about 3 minutes on it. And most of it was me just saying fast layer 3 switching, fast layer 3 switching, fast layer 3 switching. So that is the network core. All right. Whew. That was a lot in an hour. But we got it done. So hierarchical network model is, it's a framework. Okay, we diverge from this. Do I occasionally have to have a distribution layer hanging off another distribution layer? Of course. Real world does not always abide by the theoretical. And if we stay in the theoretical for too long, the stereotypes about that, the eggheads or whatever, that concept of, basically what it boils down to is they've read a lot of books, but they can't apply it in real life, and we don't want to be those types of network engineers. So, I've seen network engineers try to force this exact topology into networks that should not have this exact topology. Like, just terminate one distribution, block off another one if you have to. The internet can hang directly off a firewall that hangs directly off of the network core. That's fine. You don't need its own set of switches if we don't need it. And especially the smaller the network we get, we're going to start to collapse some of these blocks together, which we're going to talk about next week. So again, this is a framework. It's a frame of reference. It's a starting point. And if we can use this and do our best around it, we're going to end up with some really good network architectures, network topologies. So as you go out into the world for the next 2 weeks, keep an eye out. I'd love to hear some stories. Hit me up on Twitter, LinkedIn, or just bring them back to the study group in 2 weeks. Say, Jeff, I was looking at our network and I noticed that, I don't know, we've got servers hanging off our distribution switch, haha, or what have you. Whatever kind of situations. Bring your stories and tell us, hey, I saw this scenario, or this wackiness over here. We've all seen those kinds of things. And hey, if worst case scenario, you're coming back and saying, hey, I looked at my network and it's actually really well built. We want to hear that too. Let us know. So people are out there building this the right way. That's good to hear. So with that, I think that's all I've got to say. So we're going to go ahead and wrap this up here. I will stick around to answer any questions. So again, this format is I'm pre-recording this and I'm posting it up so I can participate in the chat. Format is working out well so far, so give me your feedback and comments on that. But again, I'm going to flip over here to the outro slide, and I will stay for another 10 minutes or so to answer any questions you may have. So thank you very much for joining, everyone. Again, looking forward to in 2 weeks covering enterprise network design. I will see you there. Bye-bye.